In this video, we're going to learn how to resolve the vectors that you see on the screen before you. And by resolution, I mean we're going to break them down into x and y components. Part of each vector will point in the x direction, part of each vector will point in the y direction, and then we're going to add up the parts that point in the x direction and set that aside, and then we're going to add up the parts that add up in the y direction and set that aside, and then keep those for further analysis. So in this particular problem, we have three vectors, vectors A, B, and C. And so we're going to label these. I put the measurements for each of them on the next page. So we're going to go grab those from the next page. Vector A has a magnitude of 13. So we're going to take that and put that right over here. So vector A has a magnitude of 13. And then we're going to measure this angle between vector A and the x-axis. And that angle turns out to be 22.62 degrees. And so we're going to put that in here. Move it over just a bit. Okay, so vector A is pointing above the positive x-axis at an angle of 22.62 degrees, and vector A has a magnitude of 13. Now vector B is pointing to the left, so it's pointing to the left but up also. So let's go get its information. First of all, the magnitude, or in other words size, of vector B is 8.06, and so we're going to put that in here, 8.06, like that. And then we're going to measure this angle that vector B makes with the y-axis. And that's going to help us to understand something about how we can do trigonometric analysis with this information. So I just drew an arrow pointing to that angle that we drew between angle B and, or rather vector B and the y-axis. We'll go grab that angle, which turns out to be 29.74 degrees. And we'll put that over here. So 29.74 degrees is that angle between vector B and the y-axis. Now vector C has a magnitude of 7.81. And we'll pop that over here. Right there. So that is the magnitude of vector C. And we're going to measure this angle between vector C and the negative x-axis. And the angle that vector C makes with the negative x-axis is 39.81 degrees, and we'll put that right in here. There we go. So 39.81 degrees. So we have our three vectors. We know the angles that they make with various axes, and we know their magnitudes. So now on the next page, what we're going to do is we're going to break down vector A into two components. So vector A makes an angle with the x-axis, kind of looks like this. Try that again. There we go. So that's going to be our vector A. And vector A, we're going to look at this as if it makes a right triangle. Now we said that vector A made an angle of 22.62 degrees. So I'll write that in here. This is 22.62 degrees, that angle right there. And we know that the length of that vector, or in other words, its magnitude, is 13. And what we notice is that this makes a right triangle. And as we look at this right triangle, this side over here is the opposite side, or in other words, it's directly opposite the angle 22.62 degrees. And the side down here at the bottom is the adjacent side because it's right next to the angle, 22.62 degrees. And so now we're going to use Sohcahtoa. Try writing that A again, Sohcahtoa. Okay, and Sohcahtoa is a memory aid that helps us to remember what the trigonometric ratios mean. The trigonometric ratios are the sine, the cosine, and the tangent. So S stands for sine, C stands for cosine, T stands for tangent. And the O stands for opposite. And so we see O in two places, in the sine and in the tangent. And A stands for adjacent, right? We see it in the cosine and also in the tangent. And then H stands for the hypotenuse. And the hypotenuse is the longest side of the right triangle, which in this case is 13. Pardon me. So let's use Sohcahtoa. Okay, SOH means that the sine of the angle is 22.62. I'm going to dispense with the little degree symbol, but we know it's 22.62 degrees. And that's equal to the opposite side of the triangle divided by the hypotenuse, which happens to be 13. So we do a little multiplication. We're going to switch the sides of the equation here. And what we get is opposite equals 13 multiplied by the sine of 22.62 degrees. Now I'm going to use my calculator, which is a TI 84 Plus Silver Edition graphing calculator. Not that that's particularly important. I can do this with any calculator. So I'm going to do 13 multiplied by the sine. I made sure that my calculator is in degree mode because I'm using degrees to measure the angles. So I have 13 times the sine of 22.62 degrees. Hit enter, and I get 5.000028285. And that actually, 5.0000, is close enough that we can round this off to be 5. Okay, so we use Sohcahtoa. We use the SOH part of Sohcahtoa to get the sine is equal to the opposite over the hypotenuse, and we use that to figure out what the length of the opposite side of the triangle had to be. So now we're going to do the same kind of thing, only this time we're going to use ka for the cosine. And so the cosine of 22.62 degrees is equal to the adjacent side of the triangle divided by the hypotenuse, which is 13 again. And then we're going to multiply both sides of the equation and swap the sides of the equation. We get adjacent is equal to 13 multiplied by the cosine of 22.62 degrees. And we'll multiply this out on the calculator again. We have 13 multiplied by the cosine this time of 22.62 degrees. And that turned out to be 11.99998821. We can round that off to 12. So there we just figured out the components. Now the adjacent side of the triangle points in the same direction as the x-axis, so that's going to give us our x component, which I'm going to abbreviate as x component, XCOMP, short for component. Okay, actually maybe I should write that out. There we go, x component. On the other hand, the opposite side is in the y direction, it's vertical, and so that's going to be the y component. Now another thing to notice is that in this case the adjacent side sort of points to the right, which is the positive direction. So that's going to be positive 12 is going to be our x component. And likewise, the vertical component points up, which is the positive direction. And so positive 5 is going to be our y component. Okay, let's go back and look at our diagram again. The next angle, or the next vector rather, that we're going to look at is vector B, and it has a magnitude of 8.06, and it makes an angle of 29.74 degrees, but this angle is made with the positive y-axis. So let's go over here. We'll make an axis that looks kind of like the positive y-axis, like that. Okay, and then we're going to, actually I want to make it a little bit farther down. There we go. Kind of looks like that. Turn it into a right triangle. Okay, we know that this angle here, let's go back and look at it again, was 29.74. degrees. We know that the length of the vector is 8.06, the magnitude. So that's 8.06. And so now here we have the opposite side, which is opposite the 29.74 degree angle. And we have the adjacent side, which is right next to the 29.74 degree angle. So once again, we are going to use Sohcahtoa. Okay, and let's start with the sine like we did before. Okay, the sine of 29.74 degrees is equal to the opposite divided by the hypotenuse. In this case, the hypotenuse is 8.06. So once again, we're going to multiply and rearrange, and so we get the opposite is equal to 8.06 multiplied by the sine of 29.74 degrees. And we'll use our calculator again. We're going to do 8.06 multiplied by the sine of 29.74. And that turns out to be 3.99828, etc. Now 3.99, that's close enough to where we're going to call it 4. Come back and think about that again in just a moment. Okay, so now the cosine. Okay, the cosine of the angle 29.74 degrees is going to be the adjacent divided by the hypotenuse. And again, the hypotenuse is 8.06. So we're going to multiply both sides of the equation by 8.06, and we're going to flip both sides of the equation so that we get the adjacent on the left side. So we get 8.06 multiplied by the cosine of 29.74 degrees. And we're going to multiply that out. So that's what our adjacent is equal to. So 8.06 multiplied by the cosine of 29.74. And that turns out to be 6.998, etc., which we can round off to 7. Okay, now notice this. Notice that the opposite side of the triangle, okay, that's the opposite side of the triangle up here. That opposite side of the triangle is horizontal. So in other words, it's in more or less the same direction as the x-axis. So that's going to be our x component. And furthermore, we notice that it's not pointing to the right, it's pointing to the left. So since it goes to the left, we're going to make it negative. So our x component for this vector b, this is vector b, the x component is -4. On the other hand, the adjacent side goes up, so consequently it will be positive, and that's going to be our y component. There we go. So that's our analysis of vector b. So now let's go back and look at vector c. There's vector c pointing down to the left. It has a magnitude of 7.81, and the angle is 39.81. Okay, so let's go draw a picture of it. So here's the x-axis, and vector c points down to the left like that. I'm going to turn this into a right triangle like that. Okay. That's our right angle there. Okay, and this angle in here, let's go back and look at the numbers, 39.81, 39.81 degrees. And we also know that the magnitude is 7.81. Sorry about flashing back and forth like that there, but there we go. So the hypotenuse of this right triangle is 7.81. The angle with the x-axis is 39.81 degrees. Okay, in this case, the opposite side of the triangle is this vertical component, and the adjacent side is this horizontal component, and this is vector C. Okay, and once again, we're going to use Sohcahtoa. Whoops. Okay, so once again, we use Sohcahtoa. And so let's start with the sine, like we did before. So the sine of 39.81 degrees is going to be equal to the opposite divided by the hypotenuse, and the hypotenuse is 7.81. So we multiply both sides of the equation by 17.81, and we get that the opposite side of the triangle is equal to 7.81 multiplied by the sine of 39.81. Is that correct? Yep. They have the same two digits as their last digits. Okay, so anyway, we're going to multiply those numbers now. So we multiply 7.81 by the sine of 39.81, and we get 5.00003, so we can round this off to 5. We'll come back and discuss what that means in just a moment, like we did with the others. Okay, now we'll look at the cosine. The cosine of 39.81 degrees is equal to the adjacent side divided by the hypotenuse, which is 7.81. So the magnitude of the vector A, or vector A or B or C, the magnitude of each vector turns out to be the hypotenuse of the right triangle that we're associating it with. So in this case, the hypotenuse is 7.81. So now we multiply both sides of this equation by 7.81, and we get that the adjacent is equal to 7.81 multiplied by the cosine of 39.81 degrees. And we multiply that on our calculator again. So 7.81 multiplied by the cosine of 39.81. And we get 5.9999, which rounds off to 6. Okay, now since the adjacent side is in the x direction, we know that that's going to give us our x component. And since the opposite side is vertical, we know that that's going to give us our y component. Now also, notice that the adjacent side of the triangle doesn't point to the right in this case, it points to the left. So that means that our x component is going to be negative 6. Likewise, for our y component, it's pointing down, so the y component is going to be negative 5. So to summarize, go back to vector A, we got our x component, which was positive 12. Our y component was positive 5. For vector B, our x component is negative 4, and our y component is positive 7. And for vector C, our x component is negative 6, and our y component is negative 5. Now, we can now go and summarize all of this information by making a table. And our table is going to have 3 columns. We'll figure out how many rows it has in just a moment. So we're going to list our vectors, and then we're going to list our x component and our y component. And I'm abbreviating component to fit them into the table headings. Okay, so the vector. Now, vectors can be any quantity that involves magnitude, or in other words, size, right? Like each of these vectors that we've been talking about so far have their various sizes. And they also have direction. They're pointing in a specific direction. We can analyze the direction using angles like we've been doing so far. So vectors can include things like force. Force is a vector. Acceleration is a vector. Displacement is a vector. Velocity is a vector. Magnetic field strength is a vector. Electric field strength is a vector. Gravitational field strength is a vector. There are so many different quantities that are vectors, and that's why this method of analysis is so very helpful, because we can analyze a lot of different situations the same way we're doing this problem right here now. So first of all, vector A. Turn that into a row of then we're going to have vector B. Whoops. And then we're going to have vector C. And then all of this is going to add up into something called vector R. And vector R is what we call the resultant vector. Or in other words, it's the result of what we get when we add these 3 vectors together. Okay, and so we're going to see what these turn into. So let's go back and grab the x and y components. The x component is positive 12 for vector A. Positive 12, the y component is positive 5. So 12 and 5, and we know both of those are positive. Vector B, the x component is negative 4, the y component is positive 7. So negative 4 for the x component, positive 7 for the y component. And then vector C, both components are negative. The x component is negative 6, and the y component is negative 5. So negative 6 and negative 5. So to get the resultant, what we do is we just add these together in each column. Okay, I'm going to add negative 6 plus negative 4 is negative 10, and negative 10 plus 12 plus positive 12 is equal to 2. So that's the x component of the resultant vector. And by the way, when you add 3 vectors together, you get a vector, right? Which is good to know. All right, and then adding the y components together, 5 plus negative 5, they cancel, and so the end result is 7. So that means that our vector R is equal to this result, which is we're going to write it as 2, 7. So that's what our resultant vector is. So let's say a little bit more about our resultant vector on the next page. Okay, we're going to draw another coordinate axis system. Here's our y-axis. Here's our x-axis. Let's label those. X-axis, y-axis. Okay, and we said that the resultant vector was equal to 2, 7. So what that means is that we start from the origin and we count 2 to the right. So we're counting in the x direction 2, and then we count vertically 7. So we go up 7. 1, 2, 3, 4, 5, 6, 7. Let's make a mark there. Okay, so that's the location. And then we're going to connect that to, if this thing lets me do it. Let me try this again. I'm going to draw a dot here, down here at the origin. Okay, and so now I'm going to connect those dots. This program is a little bit finicky. Okay, so this is the vector r. This is the resultant vector. Okay, and as we just mentioned, okay, this portion is 2, and this portion over here is 7. So the horizontal part is 2, and the vertical part is 7. And we're going to figure out what this angle is. We're going to figure out two things. We're going to figure out the angle with respect to the x-axis, the positive x-axis, and we're also going to figure out the magnitude of this vector. The magnitude is going to be easy, but here's how we figure out this is how we figure out the angle. Now, and to do it, we're going to use Sohcahtoa once more. Okay, and in this particular instance, we're going to use the toa part because the toa uses the O, which is opposite, and A, which is adjacent, and those are the two sides of the triangle that we have. We have 2 and 7. 7 is the opposite, and 2 is the adjacent. And T stands for tangent. So we're going to write this. We're going to write tangent of the angle theta is equal to the opposite, which is 7, divided by the adjacent, which is 2. Okay, and then we're going to perform a certain almost magical trick. What we're going to do is take the inverse function of the tangent on both sides of this equation. We're going to write this as theta equals the inverse tangent. Okay, so that tan negative 1, okay, that's tangent with a superscript of negative 1. That's not an exponent. That is not an exponent. That's a designation indicating that what we're talking about here is the inverse tangent. So an inverse tangent turns out to be an angle. So we're trying to figure out what angle theta is, and the inverse tangent is going to give that to us. And it's going to be the inverse tangent of 7 divided by 2. So we're going to use the calculator to do this one more time. Okay, the calculator I'm using has an inverse tangent button. All I have to do is push the second button, which is a blue button in the upper left-hand corner of the calculator, and then I push the TAN button, but what I'm activating is the TAN negative 1 that's printed above the button. Okay, and it's going to be the inverse tangent of 7 divided by 2, and I'll hit enter, and I get 74 degrees, 74.05 degrees, we'll call it. So that's the angle, or in other words, direction in which the resultant vector is moving or pointing. Okay, now the next thing that we're going to do is we're going to find the magnitude of the vector r, and we do that by using the Pythagorean Theorem, which means that we're going to take the square root of 2 squared plus 7 squared. So this is the same thing as the square root of 4 plus 49. And that's the same thing as the square root of 53. And that we'll calculate on the calculator. So we're going to do the square root of 53. And that turns out to be, I'm going to say that's approximately equal to, and notice I'm writing the letter R without an arrow above it. When we write the letter without the arrow above it, that means magnitude. Whereas the letter R with the arrow above it, like what we have up here, right? The letter R with the arrow above it means that we're talking about a vector. And then the letter R without the arrow above it means we're talking about a magnitude. So the square root of 53 is approximately equal to 7.28 units. And So we're going to round that off to 2 decimal places after the decimal point. And that's why we're using the approximation symbol, right, rather than an equal sign. We're using approximately equal to, because we rounded it off. This is not exactly the same thing as square root of 53. It's really close, but it's not the same thing. So the magnitude of this vector is approximately 7.28 units, and the angle at which it's pointing is 74.05 degrees above the positive x-axis. So hopefully this was helpful to you. I hope that this helps you to solve future problems.